Hello there. Like she said, I'm Noah Kantrowitz. I'm an SRE at Geomagical Labs. We do computer vision and augmented reality stuff for IKEA, but I'm not here to talk about that. Hello World is a starting point. For most discussions, it's a gentle introduction to making Python do anything at all. From Hello World, we could build towards talking about functions and strings and all of programming, but we're going to use it as a starting point for something else. Rather than looking outward at programming in general, let's look inward down the stack at the moving pieces involved in this innocuous line of code. To set the stage a bit, we're going to look at the specific case of Linux and glibc. Python runs on many platforms and combinations, but we want to look at specifics, so we need to pick one. This is the most common. All code samples I'll show will be accurate as of writing in September 2025. And our point of departure. We are in a Python interactive shell. We have typed in print hello world, and we have just pressed enter. What happens next? Not just saying it prints hello world, we know that. What really happens next? This is our first stop, slightly simplified. At heart, the interactive shell is a while loop calling the input function and then doing something with the string that it receives, specifically passing it to that push method. So the variable line will have our code, print hello world, then what's next? Every one of these layers is going to involve a lot of calls, so I'm going to skip around a bit or it would take hours. I will try to show the important parts of the call stack along the top every time. So following down from that push method, this is the part we care about. We have our code, and we're going to call the exec function on it. This is going to parse and execute our line of code. So of course, the next question is, how does that work? It's theoretically possible to build a language which executes programs just one byte at a time, but this makes any complex syntax very difficult, verging on impossible. So basically, every major language goes through a number of steps, each giving us a bit more structure than the last. Decoding bytes to Unicode characters technically happens first, but that's been covered many times in many places, so let's look at the rest of these in a little more detail. Lexing or tokenizing, two words for the same thing. I'll probably switch back and forth, I apologize. That's the step which goes from a string of characters to a sequence of tokens. Parsing turns those tokens into a syntax tree, and compilation turns a syntax tree into opcodes. To actually reach the lexer, we need to jump a ways down the stack, and in actual usage, the lexer is, despite being in C, more like a Python generator. It generates tokens one at a time as the parser asks for them, but this function, tokeGetNormalMode, is the bulk of the logic. This function goes through the characters and groups them together into tokens and slaps a label on them with whatever kind of token it is. The token module in the standard library shows you all the available token types, and we can see a few things in here. The main kinds are names, which is absolutely anything that looks like an identifier, numbers and strings, which are literal values, syntactically significant punctuation, parentheses, operators like plus or minus, colons, which are a very important one in Python. It also generates indent and dedent tokens so that the parser doesn't have to worry about tabs versus spaces, and this is the point in the process where line continuations get expanded, again, because we don't want our parser to have to worry about those. The tokenize module lets us experiment with the lexer on the command line, so let's feed it our line of code, and we'll get back 6 tokens. So the first one is a token of type name that matches the 5 characters P, R, I, N, and T. Then we have an lpar, left parenthesis token, which matches a single character, and so on, a string token, a right paren token, a new line token, and finally an end of input token. This is more structured than our original string, but it's still not ready to be run as code. We've still got parsing to go. The representation has so far been pretty linear. We had a sequence of bytes, then a sequence of characters, and now a sequence of tokens. But when we think about complex code, it's not really flat. The body of a function is, in a lot of respects, inside the function definition, or the parameters to a call are inside that function call. An abstract syntax tree extends this idea. It builds a nested tree structure that encodes all of the syntax in your code. Python's parser is built around a parsing expression grammar, or PEG input. This file, python.gram, defines the syntax of Python in terms of the tokens we were just talking about. Parsing is an incredibly dense topic. It could be a whole talk unto itself, but the short version is each grammar rule in this file matches some tokens from left to right in the correct order and produces a syntax node, and those are combined recursively to build the final AST for the code. As with the tokenizer before, the parser also has a command line tool you can play with. So we can see here when we run the AST command on our code, we get back a module with a body that is a single expression. That expression is a call of some kind, something called print. We don't yet know what that is. It's just a function call to something named print with a single argument, which is the constant value hello world. This is now fully structured and ready to proceed forward on its journey towards running. Many words have been said over the years about whether Python is or isn't an interpreted language or a compiled language, and honestly, I've mostly lost interest in the debate, but we can now show really clearly Python is a compiled language because our next stop is the Python compiler. So at this point in the code, PyParser AST from string has given us back an AST for our module, and we're going to pass that to the function runMod, and we're going to spend a lot of time in that, so get used to it. Before we can talk about compiling Python, though, we need to talk about what that compiler is for. Now, when we compile C code, we're turning the C code into CPU instructions for the physical silicon CPU in your computer, more or less. CPython has its own virtual machine, though. It's not a virtual machine like the VM on your computer that runs Windows. That's emulating real physical hardware. Instead, this is a much more abstract device. It's going to be some kind of virtual computer that we can do operations on. Specifically, it is a stack-based computer. If you've ever worked with Forth or an RPN calculator because you are old like me, that might seem familiar. In a stack-based system, there's really only three kinds of operations. You can push something onto the stack, you can operate on the top of the stack, or you can pop something off the stack. CPython also does track a couple extra things like call frame information and thread state, but the heart of it is the stack. Because our virtual machine can be way more complex than a physical CPU, we don't need to build this out of actual metal, it can have a lot of low-level instructions that are specific to Python's patterns. These are called opcodes, and they're the building blocks for all of Python. The dis module documentation lists all of them, but here's a few just to set some flavor. You can see some like load const that are really generic, and some like import name that are vastly complicated Python semantics that you could, again, spend an entire talk on. New opcodes get added as new features are added to Python. Old ones get removed. For example, 3.14, which released last week, removed the return const opcode in favor of doing a load const and a return. But at any given time, there's about 100 opcodes in Python. Okay, we're back to runMod, and we're calling down into the compiler. The core of the Python compiler is basically a visitor pattern. It's going to walk down the syntax tree. It's got a callback for each type of node in the syntax tree, and each of those callback functions is going to emit opcodes and add them into an array in a code object. And again, the compiler could be a whole talk, but let's just look at our bytecode. Like the two we saw before, the dis module is a command line interface to play around with Python bytecode. So we pass it our hello world, and we see it turns into these opcodes. So it's going to first load something called print onto the stack, then it's going to push a null because print doesn't take a self parameter, and we always have to include that. Then it's going to load a constant value of hello world, then it's going to pop the whole lot of that off the stack, do a function call, and push the return. Then we're going to pop the return value off because we don't actually care about it, and finally we're going to return none. Finally, this is a program we can run. Okay. Let's go back to runMod. So this time we've got a fully compiled code object. We are looking for the part of Python which actually runs our bytecode. This leads us to the very wordy named PyEval, eval frame default, which is possibly the most complex C function in all of Python. This function and its friends are the heart of Python's executor, unpacking each opcode, doing whatever computation it requires, and then returning to the next. This example here shows a bit of how the load name opcode works. So you can see it's got some weird stuff dealing with stack pointers at top, and then it figures out what name it's supposed to be loading by getting that out of frame co names, and then it eventually calls pyeval load name and pushes the returned object from pyeval load name into the stack by adjusting the stack pointer. This is also where the JIT happens, and I wanted to show some code samples here, but the JIT is just spread over so many places, there's not really a code sample for one thing that I can put on the screen. But the quick version, whenever a jump backward opcode is run, the executor is going to check, does this look like I've run it a bunch of times recently, meaning it's part of a frequent loop? If it is, the executor is going to stop execution for a moment, snip out all of the opcodes related to that loop, convert them from opcodes into an intermediary thing called micro-ops, and then those into CPU instructions, and it's going to cram them back in wherever the original opcodes came. This is very complicated, but very useful. All right, let's execute our first opcode. We have a load name on something called print, and we saw 2 slides ago that this is going to use the function pyeval load name. In there, we see the 3 scopes that exist in Python. First, we're going to check the locals, then we're going to check the globals, and then we're going to check the built-ins. Our hello world doesn't declare any variables, either local or global, so it's got to be coming from the third one, the built-ins. And indeed, in the list of built-in methods that are registered when Python starts up, we find one up there at the top called print. So that's going to take the built-in print function, wrap it inside a function object, and stash it somewhere that it can be found in the built-ins dict. So load name is going to find that function object, push it onto the stack. Load const is going to create a string object and push it onto the stack. Then we get to the call opcode, the interesting one. It's going to pop the load of that off the stack and jump into the actual C function built-in print, or rather built-in print impl, which is where all the interesting bits are. Now, most of the code in built-in print impl is going to be dealing with parsing arguments and returning errors, but we can see some of the expected shape down here towards the bottom. It's getting a reference to something called stdout from the sys module, and then it calls write object on each argument in turn. We are 24 slides in. We've got to be close to seeing our hello world, right? All right, if we're getting a reference to standard out from the sys module, where did that come from? When any program starts, it receives 3 special, already open files from its parent. These are referred to as standard in, out, and error, and they are respectively numbered 0, 1, and 2. Python doesn't know anything about where any of these point. It's just going to wrap them in some encoding and buffering helpers and store references into the sys module at startup so they're there when we want them. Another small aside, even though we're definitely down in C code and will remain there for basically the rest of this whole talk, you will notice that a lot of it reads very similar to Python. There's some other bits too, manual error checks, ref counting macros, but a helpful trick when reading C built-ins is to mentally translate them to the equivalent Python code. All right, let's fast forward down the stack a little bit. We'll see each of those wrappers that we talked about happening in reverse, but we'll eventually end up in this function pywriteimpl. This is the core function used by all kinds of file I/O in Python, so it is absolutely covered in special cases for unusual operating systems, but fortunately Linux is pretty simple. It calls this function write with the file descriptor for standard out, which like we said before is 1. We've got a buffer with our bytes, hello world, and the number of bytes to write, 12. Remember, there's a new line. This is the outer edge of Python. We could stop here, but what fun would that be? To dive into the write function, we need to look at libc. Libc is a standardized API exposing helper methods, operating system interfaces, math functions, and lots more. Libc itself is really just a specification, though. Anyone can implement write as long as it matches this function declaration. The API has been documented and formalized a few times over the years, but the most commonly used spec these days is the Portable Operating System Interface, or POSIX. I don't know why there's an X on the end, it just is. In most cases, the implementation that you're going to be using is GNU libc, which is shortened to glibc, although for completeness, you will sometimes run into muscle libc in Alpine or Alpine container images. We're not going to be talking about that one. This is what the implementation of write looks like in glibc. So we see the expected 3 arguments, file descriptor, address of the buffer, and the number of bytes to write. But inside, this function is not really doing very much. It's just forwarding our arguments to something called syscall. What's that? Our programs cannot be trusted. All normal programs run with a bunch of hardware-level security restrictions. For example, we can only access memory that is allocated to our program. We can't just directly access some other process's memory at will. This is incredibly important for digital security. This is collectively referred to as user space. But sometimes we do need to make some kind of dangerous call, like we want to talk to hardware. So alongside our program is the kernel. You've probably heard of this at some point. The kernel is just sort of sitting there in the background running in something called kernel space. Kernel space has no security restrictions, or very, very few. It can do whatever it wants. So to go back to syscalls, a syscall is a request from our untrusted, unprivileged user space program to the kernel to say, please run this dangerous or complicated request in kernel space on my behalf. You can think of this like the window at a bank teller. You can pass them a dollar bill or a message, but you can't jump over the counter and do whatever you want, hopefully. If you're used to modern practices, you might be thinking this is a networked API call, and some operating systems do work that way, but not Linux. Instead, we are going to do some special tricks to switch the execution pointer of our program from where we are, pointing at some memory in user space, to point instead at the kernel code's memory and begin executing in kernel space. Before we get that far, glibc does have a few wrapper functions to get through. Write is a special kind of cancelable syscall. For example, you can have a blocking write with a timeout in user space. If the timeout expires, we need to abort and unwind the syscall. But eventually we get to the syscall itself, which is shown here. This is written separately in assembly for every platform that glibc supports. For x86-64, the type of CPU that we're looking at, the standard is that you put the syscall ID, which for write is 1, very simple, into the RAX CPU register. You put the other parameters of the syscall in these other CPU registers, and then you call this syscall CPU instruction, which tells the hardware to vector, or rather jump, into kernel space at a pre-prepared location. At that pre-prepared location, we land from the syscall CPU instruction, and we are now inside the Linux kernel's code in memory. There's a single landing pad for all syscalls, so it has to look at that RAX register and dispatch to the correct function, which in the case of write is going to be the function syswrite, which is really just a one-line wrapper for ksyswrite. What ksyswrite is going to do is look up the requested file descriptor in a table of open files that it's been keeping on our behalf. This is the literal definition of what file descriptor 1 means. We want the second item in that table of open files. Then we're going to pass that file struct down into a thing called VFSWrite. Just like before, we were dispatching to which syscall we are based on the RAX. We're going to instead dispatch, but it's a little more complicated one. You can see here, it's calling through that fop struct full of function pointers. So we have to figure out, how did that get populated? Roughly 1 million years ago, I said that our Python process received its standard out from its parent process at startup. In most cases, that parent would be some kind of shell, bash, zsh, or whatever, but what did it actually give us? The os.fstat method lets us investigate any open file descriptor. Looking at standard out, we see it's got a funky file mode. That marks it as a device file, or more specifically, a character device file, which is how Linux exposes device drivers. Each device file has a device number, which is broken into 2 chunks, a major and a minor. So this is major 136, minor 0. This is new information, certainly, but it doesn't yet tell us anything about what this file is. To figure out where VFSWrite is going to send our call, we need to look at device driver registrations inside the kernel. So just like when Python starts up, we registered that print built-in the built-ins dict. When the kernel starts up, any subsystem can register a major as a device driver with a bunch of function pointers in a struct. So, because our file has major 136, it is going to populate the fops value that we saw that it's going to call through with these functions. So we can see our write's next stop is tty_write. In the olden days, when you wanted to interact with a computer, it was through this thing, a modified electric typewriter called a teletype. This was a way to send input to the program by typing on it and receive output by it printing on paper. This one here is the Model 33. It was quite cutting edge for 1963, and teletype eventually got shortened to TTY because our industry has literally always been like this. I'm guessing most of you don't work that way anymore, though. No shade if you do, but usually you're going to have a software terminal of some kind, xterm, terminal.app, command.exe. But because everything on computers is built on the bones of the past, we've left all the terminal interfaces the same since the 70s and just added on an emulated version. This is a pseudo TTY, shortened to PTY. For the most part, it's just a fancy pipe. Anything that you write on one side, you can read on the other, which really means it's a shared memory buffer that one side can write to and the other can read from. And in actuality, there's several of these because there's input and output. We're ignoring input, just looking at output, so we're going to ignore the bidirectionality for the moment. But this is what standard out actually points to, a PTY device running in Unix 98 compatibility mode. All right, back to our kernel call stack. So we know VFSWrite is going to call into TTYWrite, and eventually that's going to call into PTYWrite because that's what we registered on device major 136. If we go one layer deeper, we reach this somewhat wordy TTY insert flip string flags. This is a helper method that is going to call memcopy. It's got the internal memory buffer of the PTY. It's got our bytes. It's got our count. We're getting really close. If you're familiar with C programming, you may recognize memcopy as a libc function to copy bytes in memory from one location to another. But the kernel can't depend on libc, so it actually has its own custom implementation in assembly. Now, hello world and a new line, like we said, is 12 bytes. Don't forget the new line. So it's going to end up in this section of the kernel's memcopy for x86-64. This is for copying anything between 8 and 15 bytes. It uses 5 MoveQ CPU instructions. This is the final destination for your hello world. We could go even deeper, of course, looking at what transistors implement those MoveQ instructions or how transistors work at all. Intel and AMD don't share a lot of details about how their CPUs work, so I'd have to get really hand-wavy or switch to talking about CPU architectures that no one actually uses in real life. So I think this is the deepest we're going to go for today. With the write completed, though, we're going to rush back up the stack. We're going to clean up any kernel locks, we jump back into user space, we return from libc, we finish our call opcode, our print function returns, this print function that we've been in for 19 minutes. And then the REPL is going to loop and call for more input. We know where the write ends up, but we want to see how this actually gets to our screen at some point, right? So we said PTYs are very fancy pipes. Somewhere inside your terminal program, it has the other half of the PTY, and more specifically, it's gonna have a loop somewhere that's just polling for input from whatever is running. So it's gonna make a read syscall, gonna do basically the exact same thing we just saw, call into libc, make a read syscall, call into VFS read, call into TTY read, call into PTY read, and eventually it's gonna find the exact same memory buffer where we put our hello world bytes, and it's gonna return them all the way up the stack the same way as we just did. And then eventually it's gonna have to draw them to the screen. This is an example from Xterm. You probably don't use Xterm itself, but every terminal is gonna have something like this. And so at long last, we can see our hello world exactly as expected. Simple, right? Why do we care about all of this? After all, probably everyone here could have told me what print hello world would do. This wasn't a puzzle to be solved. Programming is full of amazing abstractions. We couldn't build things without them, but there will come a day where every single abstraction will fail you. Maybe your Python programming is crashing in an unexpected way, or you need to squeeze a tiny bit more performance out of your web app, or something new we haven't even thought of yet. Everyone should always feel comfortable peeling back the layers until you find what you need. This was certainly overkill for dramatic effect, but over my career, I've needed to poke at every single one of these projects except maybe Xterm. Play with your tools, tinker, fix, and experiment. You're not a Python developer, you're an everything developer, and inside every abstraction is a new lesson to learn. Thank you very much.
Hey there, I'm Quinn. I'm a CS student, and I took an x86 class I mentioned earlier. I feel a lot of pressure to go broad and deep as a student. Obviously, we've learned a lot here. Obviously, also a lot was beyond my understanding. I have both the autism ability to like hyper focus and go super down, and then also the ADHD run everywhere thing. What should I listen to? No, I'm just kidding. But I do have that. How do you balance as a newcomer, like the breadth versus depth question? Like, is there a perimeter you should aim for before you go down?
This is where it's really important to have problems to be solving, even if they're problems you're inventing yourself. Maybe you're making a little video game. That's how I started when I was younger. But you pick some kind of problem and you go where the problem takes you. If you need to solve something by going and looking at Linux kernel code, go look at Linux kernel code. Certainly if you're, let's say, trying to figure out how do you get 3D graphics to work smoothly on a Raspberry Pi, you're probably going to have to do that at some point. Like, that is not a hypothetical. If you want to write a web app, you probably don't have to get into writing like new kernel drivers, hopefully, but go where the problem takes you.
Yeah, so interest, purpose, and problem driven as opposed to like an orthodoxy of the way to learn. Thank you.
Hi, that was incredible. Thank you. I enjoyed the little trip back to the 1960s, and it occurred to me just to ask, how much has this changed, in the last 30 years? Like, between how much of the code is the same between like Python 2 and 3 and 3.13 and 3.14?
So basically everything from the write syscall, like from the write libc function down, is more or less unchanged in decades. The Linux VFS architecture has changed a little bit over time as they add like new async file IO stuff, but we didn't really get into that, so I was just kind of glossing over it. On the Python side, changes all the time. I had to update my slides last night because the opcode display would have been wrong because like I said, they removed that return const opcode. So like little bits of it change all the time. That's not something that's really important. Like now it's load const none return value instead of return const none. But it does change, and for very good reasons. Like that was interfering with the JIT, so it had to go. So little pieces around the edges, nothing that's usually particularly major. But if you know where to look, you will see differences.
This was fascinating. Going to the microscopic level and going back up. Is this something that was done similarly when Mojo was trying to accelerate Python?
Sorry, I couldn't hear the last part.
Mojo, did they do something similarly?
I don't know is the direct answer. I would assume probably because it's got to look fairly similar. Like I said, the libc API, like the libc API definitions and how they work hasn't really changed since I don't know, 90s probably at the latest. It's been really backwards compatible since then. Any changes have been incremental and internal. So if it's doing this, it has to go this way pretty much. Like you saw, the PTY was listed as Unix 98 mode. Like that gives you an idea of the vintage of most of these internals.
Just a question from my ignorance. I vaguely recall from the last time I wrote C code that you could inline assembly, but why would you want to? Why are we looking at .c files in the kernel and they've got assembly in them?
Because for some of this stuff, like if you are literally writing memcopy from scratch, if you do it in C, it's going to be woefully slow. Like when you care about performance at the level of I need to get bytes from A to B as quickly as possible, then there's no real choice but assembly. Or like the syscall interface thing, there's no C for that. You are writing the C that is for that thing. Like libc is exposing that, so somewhere it needs to actually like call the syscall instruction, and that doesn't exist in C. Cool. Well, thank you very much.